Thank you for joining me for this next lecture in the series of the stiffness method. Now that we know the basic concepts, we will develop the stiffness matrix for a bar or truss element in its local coordinates. We start by considering an elastic bar subjected to axial forces only, a bar element. You may also see this called an axial element or a truss element. These are all the same types of element where there is only axial force and deflections in the axial direction. The formulation of the element characteristics of the bar are based on the following assumptions. Axial deformation only. The element carries only axial forces, tension or compression. There's no bending, no shear or torsion considered. Pin connections at nodes. The joints are modelled as perfect pins, so no moments are transmitted. The member is free to rotate at the ends. Linearly elastic material. The material follows Hooke's law, and stress is linearly proportional to strain. Young's modulus is constant and uniform throughout the element. Constant cross-section. A prismatic member, and the cross-section is uniform along the element length. Small displacements and rotations. The deformations are small enough that the geometry doesn't change significantly during loading, and linear geometric assumptions apply. No initial stress or strain. The truss member is stress-free in its undeformed initial configuration. This means that in this case we are talking about a two-force member with only two equal and opposite forces acting at the ends of the element, along the axis of the element. The basis for the stiffness method relies on the load displacement relationship at the nodes of each element. As we discussed in previous lectures, trusses are structural systems which consist exclusively of straight members connected at joints located at the ends of each member. Trusses are only loaded at the joints. Since all the joints are pinned, members of a truss only experience axial forces along the member. This is just like the element we're describing. So if we start off with the truss we looked at previously, which we already discussed dividing into elements and nodes, and take a closer look at element 1 between nodes 1 and 2, and assuming it has a length of L. As this is a truss element, it'll only have forces in the axial direction, and it means that displacements will also only be in the axial direction, and therefore degrees of freedom, or in other words the possible independent movements of a node, are only along the element axis. One axial degree of freedom at node 1 and one at node 2. So in this case we have a total of 2 degrees of freedom. The stiffness matrix size depends on the number of degrees of freedom. In a truss element there are 2 degrees of freedom. Therefore the stiffness matrix will be a 2 by 2 matrix. Each member of the stiffness matrix is defined as the member stiffness influence coefficient. Each of these coefficients is the reaction developed at node I due to a unit displacement at node J. Let's look at the definition more closely in our truss element. We start by applying a unit displacement U1 at node 1 while node 2 is restrained. We then hold node 1 in place. This generates forces at both nodes. This is the first column of the stiffness matrix, K11 and K21. So in each one you can see that it is first the place, so K11, the force developed in node 1 due to a force at node 1, and K21, the force developed at node 2 due to a force in node 1. Next we apply a unit displacement of U2 at node 2, while node 1 is restrained. This also produces forces at both nodes, K12 and K22, and they form the second column. Together, these coefficients form the element stiffness matrix, which fully describes how this member resists axial deformation under nodal displacements. As we discussed, the main idea of this method is to derive the load displacement relations between the displacements and forces at the end of a structural element. As we just saw, to do this, we impose a displacement at 1 degree of freedom while holding every other degree of freedom fixed, and then we fix that degree of freedom that we moved. We then find the end actions that are required to maintain this state. If we start by looking at the first case we saw on the previous slide, where we gave a unit displacement at node 1, while the second node is held in position, so u1 equals 1 and u2 is 0, as we saw, an axial force, K21, will develop at node 2. We now need to find this force caused by the unit displacement. We know from previous studies that the displacement is PL divided by EA. If we isolate the force and substitute u1 for 1, we can then find that the force required to create a unit displacement is EA over L. Using equilibrium, we can then find the force at the other end of the beam. We'll note that it is EA over L as well. Note that the signs plus and minus correspond to the directions of the degree of freedom that we determined as positive directions. In member stiffness influence coefficient terms, K11 is the reaction at node 1 due to a unit displacement at node 1, and K12 is the reaction at node 2 due to a unit displacement at node 1. Similar to what we did on the previous slide, we now need to do the same thing for the second node. So we give a unit displacement at node 2 and hold the other node. So in this case, u2 equals 1 and u1 equals 0. As we can see, we can derive the result in the same manner, and K12 equals minus EA over L. We can then calculate the force at node 2 due to equilibrium and find that K22 is EA over L. So once again, in member stiffness influence coefficient terms, K12 is the reaction at node 1 due to a unit displacement at node 2, and K22 is the reaction at node 2 due to the unit displacement at node 2. And now we can take those results and add the terms for the stiffness coefficients into the stiffness matrix for a bar or truss element. And that's it. We have derived the stiffness matrix for a bar element or a truss element in its own local coordinates. As you can see, all the terms are EA over L, just pluses or minuses, depending on how the directions are related to what we determined as positive directions. As I mentioned in the introduction, we will be implementing the stiffness method using the matrix approach, taking advantage of the mathematical solvers that exist. As I mentioned already, my go-to is MATLAB. I have a subscription through my place of work, but an excellent and free alternative is GNU Octave. Free to download, so you can join in the coding aspect as we go through this series of lectures. It's a convenient command line interface solving linear and nonlinear problems numerically, and it can perform other numerical experiments using a language that is mostly compatible with MATLAB. You can find out more on their website, and as they're compatible and very similar in look, I will be using them both interchangeably throughout this series. In these lectures, I'll present the code for each relevant part on screen, and I'll explain it as we go through the code. If you want to join me for a session where we type the full code together as we go along, look out for a dedicated lecture on this. From here on, we'll be looking at the script notation. The percentage sign means that it's a comment, a non-executable line. We start off, as you can see here, with clearing everything. And this means that if we already ran the program and we're tweaking it, we'll not risk having any variables from previous runs stored. So you can see here, I'm preparing the file, I clear all the variables, I close any open windows, and CLC, I clear the screen. As you can see here, each command ends with a semicolon. In step 2, we need to define the material properties, E, A, and L for our single element. We need to be careful that we're consistent with our units. So here I'm going to work in newtons and meters. So I guess the most important bit here is decide what units you're using and then make sure that you're consistent throughout your program. To define the local stiffness matrix, we first need to create the stiffness matrix. We make sure it's the right size. It's a matrix of 2 on 2. And we need to ensure that all the terms are zeroed. So you can see here in this reset the local coordinate stiffness matrix, I've got K truss equals zeros, size of 2 on 2. We then enter, on the line below, the terms that we discussed for each member stiffness influence coefficient. You can see here that a matrix is bounded by these square brackets, and each row of the matrix is separated using a semicolon. So you can see here I've got my EA over L, and then I multiply it by the matrix that we developed of row 1, 1, minus 1, and then row 2, so semicolon, row 2, minus 1, 1. So this is just the full code that we just went over, and once we're happy with the code, we can press on this green Run triangle. And at this point, we can view all the variables that we generated using our code in the workspace on the left. You can see here that we've generated the A, the E, the L, as well as the 2x2 stiffness matrix for the truss element in its local coordinates. And just to finish off, this is exactly the same script. You can see the same notation, same everything in MATLAB. So you can see here, very similar interface and exactly the same code. Thank you for joining me. I hope you've managed to understand how to build the stiffness matrix for a bar or truss element in its own local coordinates, and perhaps even code it. Join me next time as we add on some more complexities to build a stiffness matrix for a beam or frame element in its own local coordinates. See you then!